Hi there. Welcome to Exactly Once Made Easy, transactional messaging in Apache Pulsar. My name is Addison Hyam. I'm the chief architect here at StreamNative. I'm a Pulsar committer, previously at Instructure, where I was a software architect there. And with me, I have CJ, and I'll let him introduce himself.
Sure. My name is CJ Guo. I'm one of the co-founders and CEO of StreamNative. I'm also the PMC member of Pulsar and Bookkeeper. Have been working on these two projects almost since from day one, and have been helping a lot of Pulsar users adopting Pulsar to solve their business problems. Prior to StreamNative, I was one of the co-founders of Streamlio. And prior to Streamlio, I led the messaging team at Twitter, where I run one of the largest Bookkeeper deployments in the world.
Thanks. And we're CJ and I, we're both from StreamNative, and just to give you a bit of background on StreamNative and what we do, we're founded by some of the original developers of Apache Pulsar, and we provide a cloud-native unified messaging and streaming platform that's designed for multi-cloud and hybrid cloud strategies. So that takes sort of form in two main products. Our StreamNative Cloud, which is a fully managed SaaS offering of Pulsar that's either running in your cloud accounts or in StreamNative cloud accounts, and StreamNative Platform, which is our self-managed software solution. We'll talk a little bit more about these at the end of the presentation to give some more detail there. But today, we want to talk about messaging semantics and transactions. And in the world of messaging semantics, there's sort of three main semantics when we're talking about messaging: at most once, at least once, and sort of the holy grail of what we're looking to do, exactly once. We'll talk a little bit more about what these mean, but as well as how transactions brings more power there. And to give some context on where Pulsar stands today, at most once and at least once have really been there since Pulsar was released. Those are the common day-to-day that everybody's very used to of using Pulsar, of being able to do these at most or at least once mechanisms. But there's actually been some support, some limited support for exactly once for a few years now through the Idempotent Producer or the producer deduplication. You'll see that reference both in the docs. That's been there since the Pulsar 1.20 release. And for more details, you can see this pip 6 that talks in detail about that guaranteed message deduplication. And so once again, before we dig into transactions, we really want to cover what these existing semantics are, the guarantees, and frame why transactions can be such a helpful new capability within Pulsar. But first, once again, we'll talk about these, and we'll frame that with where at most and at least once where these problems sort of arise. So first, let's just put ourselves in looking through a simple producer producing messages. So a producer is going to send a message, send M1 here, message 1. That's going to be received by the producer, or excuse me, by the broker, and then will be forwarded on to the underlying actual topic. In our case, that's Apache Bookkeeper, where that message is written to disk. It's then acknowledged back from the underlying segment storage into the broker, and the broker more or less forwards that acknowledgement onto the producer. And that's all well and good. I think this is the happy path here. But now let's send message M2. So we're sending that next message onto the broker. It forwards that onto the underlying storage, appends that. The acknowledgement makes it back up to the broker, but then disaster strikes. For some reason, we don't get the acknowledgement back to the producer. Various reasons why this could happen. This could be due to a producer crash, a client crash, but suffice to say, our producer never got that acknowledgement. And so the producer is left wondering, well, what do we do now? And depending on the choice of this, what the producer does, this is where we get our at least once or at most once semantics. And so first we'll talk about at least once. And in this mode, sort of the only logical thing to do is to send the message again. So we send the message again, the broker receives that, it appends that message into the underlying storage. But oh no, now we've introduced duplicates in our system. Our consumer is going to get 2 instances of M2. Depending on sort of the application, that may actually be very difficult to deal with that duplicate data. And so once again, why are these duplicates introduced? As we already sort of alluded to, there's many reasons why this can happen. The most common being, brokers fail. So a broker has a crash, the cloud strikes, and we end up with a node that's getting restarted, and that broker was never able to send that response. But it also can happen at many places along sort of the network path there. So our TCP connection dies. in flight that connection never made it. We had to reestablish connection, and depending on kind of how that message was sent, we may not be able to know that that packet was. We are not able to just resend that packet automatically, right? With a TCP connection 9, we don't have that state, and so that's one instance as well as where we can have network failure. And then finally, we also can have our applications, our producers, our consumers. Those can fail, and then we once again don't receive that message. And so, regardless of the case, if we're looking for at most once, this is quite a bit simpler. We just say don't resend. We've sent the message once. We're not sure if we got it, but we'd rather deal with missing data rather than duplicate data. So we're just not going to send the message again. And that's really where the at most semantics is very simple, has some utility, but in many cases we prefer at least once in many cases. And that's actually the default of what Pulsar is going to make happen. Is it's going to send the message again. If you want to have an at most once semantic, you have to opt into that to not do automatic retries. And additionally, now we're in this situation where I want exactly once, and we need that maybe for some application reasons. Maybe it's difficult to deduplicate data. There's lots of reasons why that exactly once semantics may be very, very useful, very, very important for application. And so that's why since that Pulsar 1.20 release, there's been some support for limited exactly once through what we call this idempotent producer or message deduplication. And as well, it's not just on the producer side. We also need to think about the consumer and how a consumer is able to get exactly once consumption. Instead of, if a consumer fails somewhere in between of its processing, making sure that it can resume exactly from where it expects to and only see the next messages. We'll talk a little bit about how that works. So once again, we'll walk through this idempotent producer deduplication, how that works. And the requirement for that is we need a few additional pieces of information. So first, we need the producer name. This is a name that we give to our producer, how that is going to be consistent between different sessions of that producer connecting. So if we have an application that it may restart, we actually want to make that producer name be the same name wherever possible. Additionally, and that identifies once again the producer. There's also the sequence ID, and this identifies the individual message within that producer. And so together, the producer name and the sequence ID, these form a unique identifier for a message. And one more note on that sequence ID, the sort of sequence, we mean that it's monotonically increasing. That sequence number always needs to be going up. And so the way that this works is the broker maintains a map between the producer name and the last produced sequence ID. And a broker will accept a message if the sequence ID is larger, strictly greater than the last produced sequence ID. Whereas if the other case where it's either less than or equal to the last produced sequence ID, it's going to discard that message. And this data, this map between producer name and last sequence ID is stored in memory, but then also serialized periodically to a deduplication cursor that's stored in Bookkeeper. And that's what allows us to have that data be moved from one broker, from one broker to another in the case of failure, etc. And so to walk through that a bit more visually, let's repeat that situation. Now we're sending, but instead of just sending our message 1, we've also added the sequence ID here. So now we're sending message ID 1 with sequence ID 1. Like before, the broker gets that message, it persists that to the underlying topic. We get, and then we do the same thing. We repeat that process for message 2. Let's just say that we're kind of skipping over that additional send there. All those acknowledgements happen, but once again, now we get that, we don't get that acknowledgement. So what do we do now? Well, now we send again, but the producer is going to look and say, hey, I've already seen sequence ID 2. This is a duplicate sequence ID. It's not strictly greater than. Therefore, I'm going to detect that duplicate and not write that, persist that to the underlying storage, but I am going to acknowledge that message back to the original producer. And this allows the producer to still get the data that it may have missed on the acknowledgement, so it can continue forward now knowing that it's received, that message has been completely written. And once again, you can enable this exactly once. And this is really, in many cases, what we still suggest. We'll talk once again about transactions, but in many use cases, this is actually sufficient and is less complex and has high performance. But so to talk about how that works is we enable this deduplication, and this can be done via a namespace policy. So we use the Pulsar admin tool. We set the deduplication on a given tenant namespace. But there's also some needs on the client. First, we need to set that producer name. So that's once again, making sure that you're using like a stable name producer. And ideally, you specify your own sequence IDs when you're producing those messages. If in your application, let's say, for example, maybe you're taking data that's coming from an auto-incrementing key in a relational database, that's a perfect number for like a sequence ID there, is an example. But any mechanism that you sort of have to be able to provide that, that's really ideal in the sense that if your application fails and you get a stable sequence ID, that producer deduplication is still going to continue to work. If you can't do that, you can still get some limited functionality out of producer deduplication for broker crashes or TCP connections, as the Pulsar client is actually going to generate a sequence ID for you and will keep a stable sequence ID for the lifetime of that producer. So once again, the difference there being, if you want that to persist against broker crashes and be safe against that, you can set your own sequence ID. But if for some reason that's difficult or you don't do that, you will at least get some producer deduplication within the lifetime of that producer. And so just to kind of also round out this idea of, we talked about exactly what's producing. That's really where a large portion of duplicates can be introduced, but it's also a concern at the consumer. And so without transactions, we'll talk about what transactions bring here today. An exactly once consumer allows you to a technique of that you can have more fine-grained control over basically the consumer reading data. And so as an idea here, the consumer, and this is often done using the reader API in Pulsar, we essentially are saying, okay, I have the last message I received was M1, so give me the messages after M1. And so the broker is going to dispatch that message. And when we receive that message, we're storing that in our local state. And next time, if we have a failure, we can start exactly from the last message we saw, M2, and we're getting sort of that, what you can think of as, we may actually see a message again, but since we're controlling the offsets, we're sort of resetting our state, and we can sort of think of as an effectively once, which often we can think of simplifies to exactly once. And so once again, these capabilities exist today. They're can be quite powerful, but there are lots of limitations. And some of those big limitations are actually when we're talking about needing to have multiple messages be delivered in exactly once mechanism. So for example, this mechanism only works when you're producing messages to one partition. So if you're trying to have multiple partition producers, or excuse me, multiple messages go to different sequence IDs, and that's like a random how you're routing to those underlying partitions, this mechanism is not going to work for you. It also only works for producing one message. So if I have maybe 5 messages that I want to make sure all get produced, that's not going to work. There's also, as we already mentioned, that limitation around the sequence ID, which there actually still is a requirement to have a sequence ID, but you can actually still have some of that more crash safety around the Pulsar client. We'll talk about that a little bit more. And really what we mean by this is that there's no atomicity when producing multiple messages to one partition or multiple messages to one partition or many partitions, right? So likewise, there's this limitation that for an exactly once consumer, we're requiring our consumers to store the message ID along with the state and then do some manual seeking back. So you sort of lose a lot of the benefits of Pulsar's consumer tracking, and you're now having to track some of that state in your client applications, which obviously brings more complexity. And so with that, we're now ready to talk about transactions, what those bring to the table, how they extend the functionality of Pulsar to cover some of those limitations and make it easier to achieve goals of exactly once using transactions. And to do that, we're going to use a sort of an illustrating example with Pulsar Cash. So this is our, we'll call it our funny money service that is sort of being able to transfer money from one user to another. And as an idea, obviously this is the kind of classic example of we want to transfer money from, user A to user B, account A to account B. And Pulsar Cache, powered by Apache Pulsar, our simple application here, is going to have kind of three main components. It's going to have a transfer topic that is a record of all of our transfer requests. And then we're going to have our cache transfer function. This could be potentially a Pulsar function or some other application that's actually going to do that cache transfer action. And then finally, we have our balance update topics. And these are the actual, these record the actual changes in balance for our underlying users, underlying accounts. And as an illustration of that, we've got our transfer topic. We're transferring $10 from Alice to Bob. We write one message to the Bob for user Bob, indicating a $10 credit and a $10 debit from the user Alice. And both of these are then written and then processed on the back end to actually make those, do the actual physical moving of money. And then once that's done, we have an acknowledgement back to our client. But hey, as we mentioned, our acknowledgement never makes it back to the producer. So what does the producer have the option to do? Well, if it sends the message again, it's going to potentially reprocess the transfer. So now instead of $10 going from Alice to Bob, $20 is going to be moved from Alice to Bob. Or maybe even worse is if one of these legs fails, we've actually lost money out of our system. We didn't get that update to the balance update for Bob. We debited $10 from Alice and then never did anything with it. And in both these cases, Pulsar transactions are really an answer here. We'll use this example to illustrate Pulsar transactions. And with that, I'm going to hand it over to CJ, who will walk us through the full process of how a Pulsar transaction helps with this.
Okay. Thanks, Edison. So Pulsar transactions was introduced for kind of improving the reliability of writing consume, process, produce programs. Like it can be used here for improving the reliability of Pulsar cache. Let me walk you through the details. First of all, we need to understand what semantics that Pulsar transaction provide. So just as what Edson said, like before, prior to like 2.8, that you can use idempotent producers to kind of write one message to a single partition exactly once, but it doesn't guarantee that you are able to write messages to multiple messages to multiple partition in kind of in an atomic operation. And Pulsar transaction, what introduced here is it allows write in acknowledgement across multiple topic partition can happen as together. So either they all succeed altogether or they all fail. And it also provides a conditional acknowledgement to handle network partitions. That means if there are two transactions attempt to acknowledge on same master, it guarantees that there's only one transaction can succeed and the other would be above. So it would ensure there's no duplicate processing logic that will happen at the same time. And at the end, Pulsar transaction only allows consumer to read commit messages. And dirty reads can kind of are not supported in this version, but they can be added very easily if there's a requirement. So this is the transaction semantic. Now let's take a look at how we can use Pulsar API to implement Pulsar cache and how we can use transaction to improve it. So this is a kind of a code sample without transaction API. So you need input consumer to receive a transfer request from the transfer topic. And after receiving the request, it will process the transfer request and generate two balance update messages, one for the sender and the other one for the receiver. Then it will write these two messages to the balance update topic. Once it successfully writes those two messages, it will then tell the input consumer to acknowledge the incoming request. And then this completes the entire process. And this diagram demonstrates the entire workflow. The input consumer receive a message and generate two balance update requests and produced to the output topic. And after finish writes those two messages, it acknowledges the incoming messages. And now let's see how we can improve the application with transaction. And what you need to do first is you need to open a transaction. And when you open a transaction, you can specify a transaction timeout. And so that means if your application didn't commit a transaction within a given timeout, the system would automatically abort the transaction. And once you have the transaction ready, you'll get a transaction instance, and you need to associate the messages together with the transaction. So similarly, as you write the application before, you create a new message, but when you create a new message, you need to put a transaction there. And once you register the two produced messages within that transaction, then you're going to acknowledge that incoming request. And similarly, you need to put the transaction as part of the acknowledgement request. Once you have registered all the operation on the same transaction, you can then call transaction commit to commit that transaction. And pretty simple, but how does that how is the transaction is being executed? So before diving into details, we need to understand what are the new components introduced for supporting transaction. So the first component we introduce is the transaction coordinator. What does a transaction coordinator do? So transaction coordinator is actually a transaction manager coordinating, committing, and aborting transactions. The transaction coordinator is implemented using an in-memory database backed by a durable transaction log. And the transaction log is actually powered by a partitioned Pulsar topic. So each transaction coordinator is running along with one partition of that transaction log topic. So locating a transaction coordinator is exactly same as locating a partition of that transaction log topic. So this is transaction coordinator. And once we have the transaction coordinator, the second component we are going to introduce here is transaction buffer. And transaction buffer is introduced for each partition involved in that transaction. Transaction buffer is used for storing and indexing the transaction data. It's implemented using another manager ledger. So all transaction messages will be appended to transaction buffer first. And broker is going to maintain a transaction index in the memory. That transaction index is going to tell what are the messages from one given transaction. And that transaction index is periodically checkpoint to a transaction cursor. And that cursor is stored as the ledgers in the underlying storage layer, which is bookkeeper. And upon a broker crashes, the transaction index can be rebuilt by recovering the ledger for the transaction buffer. So that is the second component. And the third component is the transactional subscription state that is maintained in the subscription cursor. So prior to introducing transactions, there's only two states, either a message is consumed or not consumed. And all the requests sending to the brokers, all the acknowledgement requests sending to brokers are the best effort. So you don't expect any response. So in order to provide transactional semantic support on acknowledgement, we introduce another state called act pending. The act pending means if a message being marked as act pending, that message will not be delivered to any other consumers again until it's commit or abort. And the second thing we did for the acknowledgement is adding a response for the acknowledgement. In other words, we call it acknowledgement on acknowledgement. So now the client is able to receive the response for an acknowledgement, and client know whether the acknowledgement is received by a broker or not. So with these two change, in the broker side, we also persist the acknowledgement state into the cursor ledger. So we are able to keep the acknowledgement state persistent and be able to recover in replay from the cursor ledger when a broker is crashed. So you don't need to worry about when you try to, if you already acknowledge on the message within a transaction, if the broker crash, the state would be gone. That would be all kept in persistently in the storage layer. So that is the third component. Now we have all these three components introduced for supporting transaction, and let's put these components together. And let me explain how a post transaction is executed. So first of all, by looking into the code sample here with transaction, the first thing you need to do is open the transaction. How does that work? So the Pulsar client need to send a new transaction request to any of the transaction coordinators. So if a transaction coordinator receive the new transaction request, it will append the new transaction request to its transaction log to make sure it record the transaction ID. And after it successfully return the a record about its new transaction to the transaction log topic, then the transaction coordinator would send back the transaction ID to the client, and client would use that transaction ID for all the subsequent requests. And this would ensure a transaction coordinator is able to locate all the transaction that is distributed across different topic partition and subscriptions. So that is the first step. And the second step, once you have the transaction ID, you need to produce the messages with that transaction. So how does that work? So the produce flow is exactly same as before. However, all the send command will be associated with transaction ID. So when the broker receive send command, and it will check if there's any of the send command are associated with a transaction ID. If they do, the broker will persist the transaction message to a transaction buffer first. And at the same time, the client would also register produced partition to the transaction coordinator. So coordinator knows how to commit a transaction when a client try to commit a transaction. So this is a basic kind of operation for writing, producing master along with the transaction. But one thing I want to call out here is that the transaction, when a post client try to produce the master along with the transaction, it would set the send timeout to 0, and also associate with the would also associate with the transaction, use the transaction as the producer name to achieve idempotent producing, so you don't get duplicate master produced into the transaction buffer. So that is the kind of produce the master along with the transaction. So once we achieve that, the next step is we are going to acknowledge the master within the same transaction. And how does that work? So the acknowledgement flow is very similar. So the only difference here, the master, so when a consumer send an acknowledgement back to the broker would first mark the master as pending A. So it doesn't automatically set the master to acknowledge. And the master, so the broker will persist the pending X state into a cursor ledger. So it's able to be recovered if, when broker is crashed. So also at the same time, the Pulsar client would also register the ACT subscription to the transaction coordinator. So the coordinator also know how to commit the subscription when the client try to commit the transaction. So this is like acknowledge a master within a transaction. Now we have every operations are registered along with this transaction. We need to move to the next step is to commit a transaction. Commit transaction can be divided into multiple steps. The first step is the client will send a commit request to the transaction coordinator. The coordinator writes a record to the transaction log indicating the coordinator is going to commit a transaction. Then the coordinator will start the commit process in parallel. So it will commit the master in the transaction buffer and as well as commit the pending X in the subscriptions. So once the coordinator finish committing all the transaction buffer in the pending X subscriptions, then it will write another record to the transaction log indicating that the transaction has been committed. And at this point, the transaction has been complete. And because transaction coordinator record every step how the transaction has been executed. So if broker crash in between, transaction coordinator is able to recover and re-execute all the steps again. Now I have explained the happy path of transaction execution. Then let's take a look at how Pulsar handle failures during transactions. So first of all, the transaction coordinator may crash. And because each transaction coordinator is backed by a transaction log topic partition, so all the state updates are recorded in the transaction log. So when a transaction coordinator crashes, it can be recovered from transaction log. So you don't need to worry about any state are lost during crashes. Secondly, the transaction buffer can crash. As I probably mentioned before, Pulsar client will set the send timeout to 0 for transactions, and it will also use transaction ID as the producer name to enable idempotent producing. So it will guarantee when broker write transaction messages to transaction buffer, it doesn't result in any duplicates. And next is transaction subscription state can also crash. And because all Pulsar broker persists the transaction state for a given subscription into the cursor ledger. So when a broker restart, it's able to replay the transaction, the cursor ledger to rebuild the transaction state. So you don't need to worry about the transaction subscription state is being lost during when a broker is crashed. And on the consumer side, it will try to kind of retry until it receives a response from the broker. So lastly, transaction coordinator can crash when it tries to commit produced partitions and act subscriptions. And because as I mentioned before, coordinator record every step for executing a transaction, and that state has been persistent in a transaction log. So when the coordinator restarted, and it would replay the transaction log and rebuild the transaction state and re-execute, recommit the transactions on both the transaction buffer and subscription state. So in this way, it guarantees transaction are eventually being committed in both in all the in all stage. So now we know how transaction is being executed, and the example we showed before is an example using synchronous API. But you know, the entire Pulsar API has been designed in a way that you can use asynchronous API and synchronous API depending on how you write the application. And similarly, when we design the transaction API, we also make it pure like asynchronous. That means you can write the Pulsar cache application using asynchronous API by chain all these completable feature together. But I also want to call out with this model, Pulsar can have many open transactions concurrently that can significantly increase the throughput when you use transaction API. Now, with the introduction of Pulsar transactions in Pulsar 2.8, you are able to enhance the Pulsar cache application and implement a 5-star applications using the transaction API. And it ensures writing the balance updates and acknowledging transfer requests happen in one batch. And there's no duplicates, no updates is being lost during failures. So with the introduction of Pulsar transactions, we are making messaging and streaming become much easier and more reliable for everyone. And so with transaction being introduced in 2.8, does it mean we have completed all the tasks? The answer is no. In 2.8, we only support Java client. And there are also a lot of Pulsar clients that are written in different languages. We are going to support more clients in the coming releases. And besides kind of improving the kind of enabling the transaction in other languages, we are going to enable transactions for Pulsar functions and IO connectors. That means all the functions and IO connectors can be can leverage the transaction to like do more complicated stuff. And additionally, we also want to make KLP, MLP, and ALP implement their transaction model based on Pulsar transaction. And and I also want to point out the current Pulsar transaction only support write and acknowledgement over Pulsar topics. It doesn't support write to the state storage. As you know, Pulsar have additional components called state storage for Pulsar functions. And in the future, we are going to make a transaction also support state storage. So then it will become much easier for you to write a stateful application together with Pulsar topic and Pulsar state. And for this great work, I would like to thank you for everyone that have been involved in developing and reviewing this great work. And thanks to every Pulsar users and contributors that has been involving iterating this transaction feature. So the GA release of Pulsar transaction is available in Pulsar 2.8, and you can download the Pulsar 2.8 from Pulsar website. But you can also get it from StreamNative Cloud and StreamNative Platform, which I will be talk about them later. StreamNative Platform is our self-managed enterprise-ready software offering of Pulsar. It includes the core Pulsar 2.8 to enable Pulsar transactions. And additionally, it also includes a GA release of Kafka on Pulsar that supports full Kafka protocol, and a Kubernetes extension of Pulsar function called function mesh for serverless streaming. In addition, enterprise-grade security features includes OAuth to support structured audit log, and a set of Kubernetes operators to run and manage Pulsar cluster on Kubernetes. And altogether, we want to provide a seamless cloud experience as what you can get from StreamNative Cloud. StreamNative Cloud is our fully managed SaaS offering of Pulsar. It was built for hybrid cloud and hybrid and multi-cloud. So now you can use StreamNative Cloud to stream data across different cloud providers for building multi-cloud applications. It leverages our multiple years of experience of running and operating large-scale Pulsar deployment. And our Pulsar experts will be responsible for running and scaling your Pulsar deployment. And you can rely on us for mission critical applications. And lastly, I want to also say if you're interested in working on Pulsar, you want to kind of work together with the creators, PMC members, and committers of Pulsar to shape the future of Pulsar, we are hiring globally. And StreamNative is a fully distributed team. You can join us from any place. That's the entire talk from Edison and me about Pulsar transaction. If you have any questions, feel free to reach out to us on Pulsar Slack channel, and you can follow us on Twitter as well. Thank you.
Thank you. And I think we also have time for a few questions right now. So we'll be happy to take those questions now.